So let's look at these limits to infinity. So often when we take a look at the limit to infinity of a rational expression like this, there's kind of a tried and true method for evaluating them, which is to divide everything by the highest power of x that's in the denominator. So here I have an x squared in the denominator, that's my highest power, so I'm going to divide everything by x squared. And I can either divide everything by x squared, or you can also think of it as factoring out an x squared. It's really the same process either way, and I'll kind of show it both ways, one for the first way, problem, one for the next one. So here I'm going to divide everything by x squared. I'm going to get the limit as x approaches infinity of 2x squared over x squared plus 3x over x squared plus 5 over x squared over 7x squared over x squared minus 9 over x squared. I think it's totally reasonable to skip this step on your own. I would totally feel fine with you saying we're going to have the limit as x goes to infinity of 2x squared over x squared is 2. 3x over x squared is 3 divided by x. 5 over x squared is still 5 over x squared. And then in the bottom, 7x squared divided by x squared is 7. And we have 9 divided by x squared. And then we say to ourselves, as x gets really large, something divided by x or x to a power is going to get very, very small. So 3 divided by x is going to get closer and closer and closer to 0. 5 divided by x squared, same deal. 9 divided by x squared, same deal. So when we evaluate this limit, we get 2 plus 0 plus 0 over 7 minus 0, which is just 2/7. I want to point out, because it's important, when you evaluate the limit, like when you actually plug in and you get just numbers, we no longer write the limit as x goes to infinity here because we have found the limit. It's 2 over 7. You might notice that this kind of happens a lot when you have the same degree on top as on bottom, right? Here our degree is 2, here our degree is 2, is the highest power of x in our polynomial. When the degrees are the same, limits always, and you're taking the limit to infinity, you're always going to end up getting the quotient of the leading coefficients. So I knew from the get-go, oh, I had x squared on top and x squared on the bottom, I'm going to get 2/7. In a similar way, I'll say that later. I'll give you a short one later on. We can do the same thing here. Now, I'll point out for this rational function, we don't have the same degree on top as we do on the bottom. The degree on top is 1, the degree on the bottom is 2. So I'm not expecting my answer to be 5/3. Let's see what happens. So here, instead of dividing everything by x squared, I'm going to factor out x squared instead, just to kind of show you how that looks different. Some people prefer to do it that way. It's really the same work. Literally the same work, because if I factor out an x squared from the bottom, I'm really just dividing each of the things left by x squared. 3x squared divided by x squared is 3. 2x divided by x squared is 2 over x. 6 divided by x squared is 6 over x squared. It really is the same work. On top, I'm going to do the same thing. It's always the highest power of x that is in the denominator. So factoring out x squared on the bottom, on the top, 5x divided by x squared simplifies to 5 over x. 1 divided by x squared is 1 divided by x squared. The difference here is I have to take the additional step, or at least think about the fact that x squared divided by x squared is just 1. So those will cancel each other out. And then it's the same idea. We say, okay, as x gets very, very large, 5 over x is going to be super duper small. 1 over x squared is also going to be very small. 3 is just 3. 2 over x goes to 0. 6 over x squared goes to 0. So we end up getting 0 divided by 3. 0 divided by 3 is 0. One time when I was doing this many, many years ago, a student said, well, why don't you just write it so they both have the same leading or the same highest degree? And I thought this was a really kind of a cool trick, which I'll write up here. Someone said, you can do this. You can rewrite that problem as the limit as x goes to infinity of 0x squared plus 5x plus 1 over 3x squared plus 2x plus 6. It feels kind of like you're cheating, but it totally works. It's so it's just another way we can see, oh yeah, for this kind of thing where the degree on top is smaller than the degree on the bottom, your limit's going to end up being 0 as x goes to infinity, because this denominator is getting bigger much, much faster than this numerator. Finally, the flip, and I don't know if I've left myself enough room here. I might have, we'll see. So now I'm going to divide everything by what? Sorry, say one more time. Not x squared, just x. So I know my writing. I just have an x to the first and the bottom. Oh, it's all gone. Oh well. So I'm going to divide everything by x. We have the limit as x goes to infinity of negative 2x cubed divided by x plus 5 divided by x over 3x divided by x. And this is definitely a place where I should have skipped a step. This is my room. And then continuing here, we write this as the limit as x goes to infinity. Simplifying, we get negative 2x squared plus 5 over x over 3 plus 7 over x. And now if we plug in infinity, I'm going to get negative 2 times infinity squared plus 5 over a large number gets small over 3 plus 7 over something getting very large is also going to be small. And now you have to do some kind of silly math. We're going to talk about infinity in kind of a weird way. What's infinity times infinity? Right. What, or as I would say, when you say infinity, what you should really hear is a really big number. What's a really big number times a really big number? Oh, a really big number still. What happens if you multiply it by negative 2? Well, it's still really big, but now it's negative. And add 0, still really big and negative. Divide by 3, a really big negative number divided by 3 is still a really big negative number. So we end up with a really big negative number. And that's not surprising because here we saw that the numerator was raised to a higher power than the denominator. So this thing is going to grow much faster on top than at the bottom. So the fraction is going to get larger and larger and larger, but happens to be getting larger in a negative way because we have that negative coefficient there. Let's see what the chat question or chat comment here. This is, well, yeah, that's an excellent point. Yes. So looking back at both of these examples here, we could say that from example 1, the function 2x squared plus 3x plus 5 over 7x squared minus 9 has y equal to 2/7 as a horizontal asymptote. Because this is how you find horizontal asymptotes, by taking the limit as x goes to infinity or to negative infinity. We didn't do negative infinity for any of these because it ends up being the same. But it's something worth knowing is that for rational functions, you do get the same limit as you go way, way, way out to the right, way, way out to the left. In a similar way, we could say that the function g of x equal to 5x plus 1 over 3x squared plus 2x plus 6 has y equal to 0 as a horizontal asymptote. Sorry, I know it's off the page there. Apologies. Let me scooch this over a little bit. There we go. Okay. And then thirdly, the function h of x equal to negative 2x cubed plus 5 over 3x plus 7. Well, the limit was negative infinity. Can we draw the horizontal line y equal to negative infinity? I mean, from my tone, clearly the answer is no, right? I'm asking it very much like it. That would be weird kind of way. There's no horizontal asymptote here. The function just, as you go out to the right, just keeps getting more and more and more and more negative without that. So when your limit is infinity or negative infinity, we get no horizontal asymptote. Yeah, Eric.
For like just all the columns, how do we know when to make it with 0? Like,
so yes, excellent question. So how do I know when to make it 0? So what I'm doing here, and this is kind of actually the crux of what's happening, is we are using the fact that when you take the limit as x goes to infinity of, I'm going to start off simple here, of something like 1 over x. So x is really, really big, or is getting really, really big. And when you take 1 and divide it by a really big number, what do we get? A really big number or a really small number? Right. And the way I've always kind of heard this described to me is, say you had $1, just $1, and you want to divide it among 10 people. How much would each person get? How much? 10 cents. What if I did it between 20 people? Half of that's 5 cents. What about between 200 people? Everyone's getting half a cent. 2,000 people, everyone's getting 0.05 cents. So the more and more people you divide your $1 by, the less and less and less everybody gets. So if you take your $1 and divide it by 1,000,000 people, everyone's getting a fraction of a cent. And so the larger and larger and larger this denominator gets, the smaller and smaller and smaller that fraction gets. And so I really want you all to keep in mind, because I'm gonna allude to this many times. When you have a fraction, if your denominator is large, the overall quotient is small. And on the flip side, if your denominator is very, 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 very small, getting closer and closer and closer to 0. Well, if you take a fraction and you divide it by a super small, or a number and divide it by a super small number, for example, if x was equal to 1/1,000,000th, well then 1 divided by 1/1,000,000th, what's that going to be? Well, when you divide by a fraction, we flip and multiply. So you're really going to get 1 times 1,000,000 over 1, which is going to be 1,000,000. So as x gets or I should say, as the denominator gets smaller and smaller and smaller, closer and closer and closer to 0, the overall fraction gets infinitely large. And you can see this from one of our favorite graphs. The graph of y equal to 1 over x. Has this typical shape. I'm always smearing the thing. So there's an important point at 1, 1. There's another important point at -1, -1. So you can see for this graph of y equal to 1 over x, as x gets really, really, really big, the y values get closer and closer and closer to 0. As x gets very, very close to 0, the y values get infinitely large. I should have said, as x gets really, really close to 0 from the positive side, the y values get infinitely large. And on the other side, as x gets really, really close to 0 from the left side, the y values get very, very negative. And as x gets very, very negative, the y values get closer and closer to 0. Here's how we would write all of that using the notation of limits. The limit as x approaches infinity of 1 over x is 0. The limit as x approaches 0 from the right of 1 over x is infinity. The limit as x approaches 0 from the left side is going to be negative infinity. And finally, the limit as x goes in the negative infinity direction of 1 over x is also 0. Yes, of course. Sorry, I keep getting off here. I'm trying to, let's move that here. Let's see what's in the chat. Does it depend on the teacher, or do we have to show this work on a homework test? Because I just look at the X ones. So it does depend on the teacher. Typically, in your first in Calc 1 on your first exam, if they ask you a question about finding the horizontal asymptotes, about finding this limit, you are typically expected to show this work of dividing by the highest power of x in the denominator. And then after that, we typically move on. We're like, okay, when we do these limits from then on, then you can kind of just, do it whichever way you like. But usually you kind of have to show that work, I would say. The other thing I would point out is that these two things right here, that's showing us that we have a horizontal asymptote, which is y equal to 0. And these things right here are showing us that we have a vertical asymptote at x equal to 0. Because as x is closer and closer to 0, the y values get infinitely large or negatively infinitely large. Cool. Other questions about this? Yes.
Not specifically about this question, but like in your book, with the x lines, I think it was like 3x squared on top and then 3x or 2x squared on the bottom.
Mhm.
Like when, I think it's just similar to the other question, like when looking at the exponents, can you not just take the 3 over 2?
So you can't, so here's what I'll say about that. So let's say we had the limit, and again, this is only for when x is approaching infinity. If x is approaching some other number, what we're about to say doesn't apply. If I want to find the limit as x approaches infinity of something like 4x squared plus 5x minus 1 over 3x squared plus 2x plus 8, we should all be able to eventually, or maybe right now, know what the answer is going to be. The answer is going to be what lovely fraction? 4 over 3. But what I think Anthony was just asking, what I was saying is that your teacher might not be okay with you on your first exam just saying that. You might need to show the work of dividing everything by x squared and saying, okay, that's going to be the limit as x goes to infinity. And I'm going to skip a step here and divide everything by x squared and just say I've got 4 plus 5 over x minus 1 over x squared over 3 plus 2 over x plus 8 over x squared. And then we get to say, oh yeah, we know that as x gets really, really large, everybody, what happens to 5 divided by x if x is getting really large? 0, small. Same for 1 over x squared. Same for 2 over x. Same for 8 over x squared. As x gets big, something divided by x or x to a power gets very, very small. So then we're going to say this is equal to, we're taking the limit, we're no longer writing the limit, 4 plus 0 minus 0 over 3 plus 0 plus 0, which is 4/3. So even though we know what the answer is already going to be, it's usually a requirement to show this work on your first exam. Not always, but often. Let's see what we can try. Okay, we can, yeah, sure. Let's take a look at that one. I like that problem. That's a good question. So let's look at graphing this rational function. Yeah. 2x squared minus 6. Yeah, over, that's going to be interesting. X squared minus 2x plus 1. So graphing is a real kind of large bag of things that you have to consider. When I graph a function, and really what I should say is we're going to graph just a little bit, and then really you're not going to really kind of graph things in all the detail that we will eventually graph them until we have talked about derivatives and how we can find relative maxima and relative minima. So for now, when you're graphing something, here's what I would say you should focus on. We're going to focus on the intercepts, the y-intercept, the x-intercept, possibly plural because there's more than one. And then we're going to talk about the vertical asymptote and the horizontal asymptotes. Those are the only things we should look at when we're graphing functions at this point. I think there might, I don't know, there could be I guess you could consider symmetry as well, but when I'm graphing something and not thinking about taking derivatives, those are the 4 things I'm looking for: x-intercepts, y-intercepts, singular, vertical asymptote, horizontal asymptote. Yeah.
And like the roots and like the sign charts, that wouldn't be like.
So I am not a huge fan of making a sign chart for graphing a function.
Okay.
Not that you can't, but but I think we do. I think it's not always necessary. So let me show you why, and then we'll talk about that. So let's find my y-intercept. Y-intercept is usually pretty easy. We're setting x equal to 0, and f of 0 is going to be 0 minus 6 over 0 minus 0 plus 1, which is negative 6. Something else I've seen over the years is that when you're trying to deal, especially with a rational function, the y things are really nice and easy to see when you haven't done any factoring. Whereas the x things are usually easier to find if you factor this thing as much as possible. So if I just simplify this, if I factor out a 2 from the top, and the bottom does factor as x minus 1 times x minus 1, that's going to make it easier to find the x things, which are the x-intercepts and the vertical asymptotes. Okay, so x-intercepts, we set the whole thing equal to 0. So let me ask everybody, show me on your fingers. What is the only thing x is for sure not allowed to equal? Fingers. Yeah. Cool, yes, not that, no, I'm just kidding. Okay. So we know that x can't be 1. So when I do this multiplication here, when I multiply both sides by the denominator, I get 2x squared minus 3, sorry, 2 times the parentheses x squared minus 3, equal to 0 times x minus 1 squared, which is just 0. What a lot of people end up saying is that when you're trying to find the x-intercepts for a rational function, you're really just finding where the numerator is equal to 0. Because that's the only time a fraction can equal zeros. Numerator is 0 and the denominator is not. Yeah.
Why can't it equal 1?
Why can't it equal? What if x is equal to 1? What would happen? Well, if I plug in 1, f of 1 is going to be 2 times 1 minus 3 over 1 minus 1 squared, which is 2 times negative 2 over 0. What's negative 4 divided by 0? It's not 0. Negative 4 divided by 0 is undefined. There is no number. So what we're going to see in just a minute here is that we're going to have a vertical asymptote at x equals 1. Because as x is closer and closer and closer to 1, the denominator is going to get super duper small. And what happens when to the fraction when the denominator gets small? Does the fraction get bigger or does it get small? So when the denominator is tiny, the fraction is gigantic. We'll come back to that in just a second. So here, solving this is not super nice. Divide both sides by 2. X squared minus 3 equals 0. I don't really want to factor this, although you could factor it as x minus root 3 times x plus root 3. But let's just solve it by setting x squared equal to 3 and then getting x equal to plus or minus radical 3. So those are our x-intercepts, root 3 and negative root 3. There's my y-intercept, negative 6. Now we're going to find the asymptotes. Asymptotes. Let's start with the vertical asymptote. So if my function is 2 times x squared minus 3 over x minus 1 squared. The easy way of identifying a vertical asymptote in a rational function is just seeing what makes the denominator 0. I should be slightly more specific. What makes the denominator 0 and the numerator not 0? 0 over 0 doesn't necessarily give you a vertical asymptote. Not 0 over 0 does. So here we see that, if we set the denominator equal to 0, we're going to get x equal to 1. And really, when you're graphing things, that's all you need to do. But I want to be a little bit more explanatory here so we know why we have a vertical asymptote. So you get a vertical asymptote when you take the limit as x approaches some finite value, like 1, from either side. And if we take the limit as x approaches 1 from the right of 2 times x squared minus 3 over x minus 1 squared. So just like when we did, I know it's been 5 days, it's been a while, but when we did this on Thursday, we just plugged in the 1. When we plug in the 1, I know we're going to get something weird, but on top, I'm going to get 2 times negative 2. On the bottom, I'm going to get 1 minus 1, which is 0. And I'm going to ask you, since x is slightly bigger than 1, my denominator here is slightly positive or slightly negative? Slightly positive. Now, it doesn't actually matter because I'm going to square it anyway, but it's still good to think about because you're not always going to be squaring it. So here we're going to get a negative 4 over a slightly positive, very, very small number. All right, I want everyone to imagine this for a second. When you have a very, very small number, I like to think of 1/1000th or 1/1,000,000th. So if you're dividing by 1/1,000,000th, is your fraction getting large or getting small? Getting large. Now, in this case, it's going to be negatively large. And that's the verbiage I would use, right? There's not a good way to say negatively large other than saying negatively large. Some people say small, but really when you say small, I want you to think of getting closer and closer to what? 0. And when you say big, you're getting very, very big to the right. And when you say negatively big, you're getting very, very big to the left. That's the only way I can think of to say it that doesn't suck. So then what's a negative number divided by a positive number? The negative number, and it's negatively large. So here's what this tells me graphically. This tells me that when I try to graph this thing at x equal to 1, which is where my vertical asymptote is going to be, as I approach 1 from the right-hand side, my graph is going to go down, 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 down. Like that. On the other side, sorry, you can't quite see that. When I do the limit as x approaches 1 from the left of 2 times x squared minus 3 over x minus 1 squared, I'm going to get 2 times negative 2 again. And the bottom is going to be now a slightly negative number, but still squared. So I still end up with a negative 4 divided by a very, very small positive number, which still gives me a negative infinity as what my limit is. So from the left-hand side, we are also going down, 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 down to negative infinity. And I also know from before that my y-intercept was negative 6. So let's just call that negative 6 and say we're going to go down, 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 down like that. Cool. So now I have to graph the rest of this thing. And I still haven't found my horizontal asymptote. And I probably not set myself up for a lot of success here. I mean, my labels are going to look kind of weird, but it's okay. So horizontal asymptote. So we're going to do the limit as x goes to infinity of 2x squared minus 6 over x squared minus 2x plus 1. So again, I want to point out something I said earlier. When you're finding the y things, meaning the y-intercept and the horizontal asymptote, it's nicer to have the multiplied out form. When you're finding the x things, it's nicer to have the factored form. So everybody should be able to show me on the fingers, what's my horizontal asymptote going to be here? See some fingers. Cool. Yes, right on. Yeah, it's going to be 2. And I'm not going to show my work because we've shown the work enough times for that one. And I want to keep going here. So my horizontal asymptote is going to be y equal to 2. Which means that I don't know what's happening in the middle necessarily, but as you move out towards the end, and I really should say, it's also true if we do the limit as x goes to negative infinity of 2x squared minus 6 over x squared minus 2x plus 1, you would also get positive 2 as that. And I will just make the blanket statement again and again and again. For rational functions, you always get the same horizontal asymptote to the left and to the right. There are other stranger functions where you can have a different horizontal asymptote on the left and the right, but it's not the case for rational functions. So I'm just going to say, as we move to the right, I'm going to get closer and closer to that horizontal line. And same thing as I move to the left. And ignore the fact that my graph doesn't look great. No, it's really not good, James. Oh, sorry. That's terrible. And so then these x-intercepts, which I'm going to label, even though they look very, very far apart from each other, that's positive root 3. That's negative root 3. If you were doing a better job of this, you would have moved this in closer here and that further down to make it look a little bit nicer. But really, you can fix a lot of things with appropriate labeling. Your graph can look like trash, which mine kind of does. And if you label it appropriately, you can still get all the credit, in my opinion. Questions about anything I've said so far?
So we have to graph with 30 questions that we haven't tested.
Yes. Yeah. I mean, certainly there, I think this was a homework question, was just to graph this thing. So again, when someone says graph, it can really be like less involved in this or more involved in this. Like there's a whole other thing we could have done after we learn how to find derivatives. We take the derivative of this function, set it equal to 0, find some critical points, and then maybe find a relative maximum or a relative minimum. But that's a whole other story.
I know we don't need it for this one, but I'm confused when signs are helpful and how do you?
Sure. Excellent question. So let's actually we will talk about that. Sure. So yeah, fair question. So yeah, let's look at another example. So let's say I want to, yeah, sure. Let's look at f of x equal to, sure, let's do this one. X plus 1 squared over x squared minus 4. So I'm not going to lie, I don't like making a sign chart. I feel like it's way more work than I ever want to do. And I typically avoid it by using what the graph is already telling me. But we're going to make a sign chart for this one as well. But I'm going to first tell you how to avoid it, and then I'll show you how to use it. So if I was gonna graph this, and I'm gonna do this kind of quick, I'm gonna find the usual things. Y-intercept, I'm gonna set x equal to 0. F of 0 is going to be 1 on top, -4 on the bottom, so -1/4. X-intercepts. Really, I'm just going to set the top equal to 0, although I could pretend like I'm doing the first step of setting the whole thing equal to 0. But then I'm just going to say multiply both sides by the denominator. I get x plus 1 squared equal to 0. So x is equal to -1. And I might as well point out that the multiplicity of this intercept is 2. And when an x-intercept has an even multiplicity, it means you're going to bounce off the x-axis when you try to touch that intercept. Vertical asymptote, I'm going to set the denominator equal to 0. I do like factoring when it factors nicely, so I would think of this as x minus 2 times x plus 2 equal to 0. And then you're going to get x equal to 2 and x equal to -2. So you've got 2 vertical asymptotes. And then finally, horizontal asymptote. To find the horizontal asymptote, I would multiply it out. X plus 1 squared multiplies out as limit is x plus infinity, x squared plus x plus 1. And so my limit here ends up being 1 divided by 1, which is 1. So there's all of the information at our fingertips. So here's how I'm going to graph this thing without making a sign chart. So let's plot all the things I've got. There's 1, -1. So my y-intercept is -1/4. My x-intercept is -1. My vertical asymptotes are at +2 and at -2. And yeah, let's see if I want to say more about that. And then my horizontal asymptote is at +1. I mean, I guess a sign chart's not a crime. I just really lazy when it comes to it. So we can make a sign chart here. There is a way to not do it, but it involves really. So here's how you would avoid the sign chart if you really wanted to. You'd have to see what's going on with the vertical asymptotes. So like this vertical asymptote, if I was approaching 2 from the right hand side of x plus 1 squared over x squared minus 4, the top is going to be 2 plus 1 squared, which is 9. And if I'm a little bit bigger than 2, is my denominator a little bit positive or a little bit negative? A little bit positive. I know, sorry, I know I'm writing small. So over here, this is going to be a positive infinity. So as I approach 2 from the right, we're going up and up and up. And I should label these. This is x equal to 2. This is x equal to -2. On the other side of 2, as I approach +2 from the left of x plus 1 squared over x squared minus 4, the top is still +9, but now my denominator is slightly negative because I'm plugging in a number that's a little bit less than 2. A little bit less than 2 squared is still a little bit less than 4. A little less than 4 minus 4 is slightly negative. It's actually easier to see if you factor this denominator, which we'll do for the next part. But there, that means from the left side of 2, we're going to be getting negative infinity. So we're going to be going down, 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 down. I'm sorry, I know I'm kind of squeezing everything in here. If we look at -2, the limit as x approaches -2 from the right. Now I am going to factor the denominator. I'm going to write this as x plus 1 squared over x minus 2 times x plus 2. This is where I feel like things are a little bit harder to make sure that we do right. So on top, -2 plus 1 is -1. Squared is +1. On the bottom, -2 minus 2 is -4. -2 plus 2 is 0. Okay, so we're a little bit bigger than -2. Like -1.9, because that's on the right side of -2. And -1.9 plus 2 is slightly positive. So I've got positive, positive, negative. So overall, this whole thing is going to be negative. And then on the other side of -2, on the left of x plus 1 squared over x minus 2 times x plus 2, you would be getting +1 on the top still, -4 there, because -2 minus 2 is still -4. And now a number a little bit less than -2, like -2.1 plus 2 is slightly negative. So we end up with a positive over a negative times negative, which is a positive infinity overall. So at -2, on the right side of -2, we're going down, 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 down. On the left side of -2, we're going up, 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 up. So here's what I would say. You can only cross the x-axis when you have an x-intercept. Otherwise, you're not allowed, right? You can't, right? You can only cross the x-axis when you have an x-intercept. Now, so I'm going to start here. I'm going to go towards this x-intercept, but then I actually don't want to cross because I need to come back and hit that point there and then come back this way over here. And then on the other side here, I'm up there, and then I'm going to come down towards my horizontal asymptote. On the left side here, like that. That's how I would graph this. But let's talk about making a sign chart here. So let's see if we can make a sign chart. Let's see. Do I know how to make a sign chart? Probably. So sign chart for f of x equal to x plus 1 squared over x squared minus 4. There are lots of ways of doing this. I'm always trying to do as little work as possible. So I would say you definitely want to factor your function completely to make a sign chart, because the sign is always based on how many positives and negatives we're multiplying or dividing together. If you haven't factored it fully, it's kind of hard to see. So first, we're going to identify any important x value, meaning anything that either makes this equal to 0 or undefined. So basically, identify the places where you have vertical asymptotes or x-intercepts. So on our sign chart, we're looking at x equal to -1, +2, -2. Those are the important numbers on our sign chart. Notably not 0. I don't care about 0 at all. So -2, -1, +2. I really don't like writing all the factors down. You can, it's totally fine. Like you can say, I'm really so not good at this though. Like, so my factors are x plus 1 and x minus 2 and x plus 2. And then you're just going to pick a point in each of your 4 intervals. So I'm pick something bigger than 2, like 3 or 30,000. Doesn't matter. All the signs should be the same, whatever number you pick bigger than 2. So I plug in 3. 3 plus 1 is positive. 3 minus 2 is positive. 3 plus 2 is positive. And a positive times a positive times a positive. I know I said times, even though some of them are divided, but division and multiplication are really the same operation, just inverted. Positive times a positive times a positive is positive. Now I pick something between -1 and 2, like 0. What I'm really going to do is actually just look at the overall sign. 0 plus 1 squared is positive. 0 minus 2 is negative, 0 plus 2 is positive, and a positive divided by a negative times a positive overall is going to be negative. I could have written the signs here, right? X plus 1 is positive. I should have really said x plus 1 squared. Sorry about that. X minus 2 is negative, x plus 2 is positive. Moving to the left. Ooh, I got to pick -1.5. Okay. So -1.5 plus 1 is negative, but the negative number squared is still positive. -1.5 minus 2 is negative. -1.5 plus 2 is positive. A positive times a negative times positive is negative. And finally, picking something like -5. -5 plus 1 is negative. Squared is still positive. -5 minus 2 is negative. -5 plus 3 is negative. Notice, I don't pay attention to the actual values at all. I don't care that -5 plus 2 is -3. I just care that it's negative something. So don't get caught up finding the numbers, just focus on the signs. That's why it's the sign chart, not the value chart. Negative times a negative times a positive is positive. So what this means for our graph is from negative infinity to -2, the graph should be above the x-axis. From -2 to -1, it should be below. It should touch at -1 because we have an intercept -1. From -1 to 2, it should also be below. And from 2 onward, it should be above. And that's exactly how our graph looks. Come on, papers. From negative infinity up to -2, our graph is above the x-axis. From -2 to -1, below. From -1 to +2, also below. And from 2 onwards, above. There's something else I wanted to say here. Oh, so something you'll see with practice with these sign charts is that at each intercept or asymptote value, the sign is going to change if that intercept or asymptote value came from a factor raised to an odd power. And the sign is going to stay the same if that value came from a factor that has an even power. So x plus 1 squared, that's where we got the -1 from. Having an even power means when you go from one side of it to the other side of it, the sign stayed the same. -2 came from a factor that has an odd power, and that's where the -2 came from x plus 2. That odd power means the sign is going to change. It's always true. So let me give you another. Oh, sorry, there's something in the chat here. Sorry, I keep getting off to the side. Can you explain the multiplicity of 2 that I said way back when was is just the power on the factor that value is coming from. So when I said that x equal to -1 has a multiplicity of 2, it's because that x equal to -1 came from setting x plus 1 squared. The square is the multiplicity equal to 0. Let's look at another example with a slightly different kind of thing. So I feel like we should start talking about continuity, and we'll try to incorporate this. So continuity. Here's a good place to start. Most functions are continuous on their domains. I know most is not a very specific word. But it's true. Most functions are continuous on their domains. In fact, a lot of the typical functions you might be aware of are continuous either everywhere or on their domains. So a few things that are in this list are like polynomials. Polynomials, things like f of x equal to 5x cubed plus x squared minus 3x plus 4, those are continuous everywhere because their domain is everything. So are trig functions. Trig functions, sine, cosine, tangent, cotangent, cosecant, are all continuous where they are defined on their domains. For sine and cosine, that's everywhere. The sine function looks like this. The cosine function also looks like this, and they are defined and continuous everywhere. Tangent, cotangent, secant, cosecant, those all have vertical asymptotes. Those are certainly not continuous at the vertical asymptotes, but they are continuous everywhere that they're defined. A couple other fun functions. F of x equal to e to the x, everyone's favorite exponential function, is continuous everywhere. I'm just gonna say is continuous. If someone says continuous and they don't say anything else, it means continuous everywhere. And g of x equal to the natural log of x is continuous on its domain, which is the interval from 0 exclusive to infinity. And again, I'll say this many times, most functions that are quote unquote normal, typical, are continuous on their domains. Oh, the other one I should include here are rational functions. Yeah, that's interesting. sorry, rational functions are continuous on their domains. So that function that we just looked at, I'll show you the graph of it again. This function is continuous everywhere except for at x equal to 2 and x equal to -2, because those are the only two values that are not in the domain of this function. But what about something like this? What about f of x equal to the square root of x minus 2 squared plus times 3, sure, 3 minus x times x plus 4 to the third power. I will tell you also that this function is continuous on its domain, as most functions are. But the question here is then, well, if this function is continuous on its domain, what is its domain? Well, I've got a square root of some stuff. And when we take a square root, the stuff we're taking the square root of has to be not negative. Right? We can't take the square root of a negative number and get a real result. So here, we're going to say this is continuous on its domain. And the domain is going to be where the inside stuff, x minus 2 squared times 3 minus x times x plus 4 cubed, is greater than or equal to 0. And in my mind, this is where you typically would use a sign chart, is where you would find the domain of a function like this. So I'm going to make my sign chart. And if you have a different way of making your sign chart, that is totally fine. I'm just showing you the way that I typically do it because I'm me and not you. I know, big surprise. Oh, there was something fun I was going to tell you. We'll throw it in at the end here if we have time. So what numbers are going to go on my sign chart? All the values that make this expression either equal to 0 or undefined. It's never undefined. So we're just looking at the values that make it equal to 0. So on the sign chart, we want the values that make that expression x minus 2 squared times 3 minus x times x plus 4 to the third equal to 0. So what's one of the values? Sorry, one more time. Say -4. Sorry, I'm not, actually -3 is not. So if we plug in -3, what's 3 minus -3? It's +3. But I'm glad you said -3 because it's something that people often make a small error on. So if we set 3 minus x equal to 0, we're going to get 3 equal to positive x. So x is going to be 3. What's another value on my sign chart? -4. And no, be quiet. And what's not you? Sorry, my watch. And what's the last value on my sign chart? What makes this factor equal to 0? Is it +2 or is it -2? Not both. So if I plug in 2, what's 2 minus 2? 0. If I plug in -2, what's -2 minus 2? -4. So the thing, this is x minus 2 squared, which is different than x squared minus 4. If you had x squared minus 4, then you would get 2 and -2 as values that made it equal to 0. But that's very different than x minus 2 squared. X squared minus 4 is equal to x minus 2 times x plus 2, which is a different animal. So here are the 3 values that are going on our sign chart. And really, the way you can get them is just by setting each factor equal to 0. If you set 3 minus x equal to 0, you get 3 equal to x. If you set x minus 2 squared equal to 0, you're going to get x minus 2 equal to 0, which means x equal to 2. And if you set x plus 4 cubed equal to 0, you're going to get x plus 4 equal to 0, which gives you x equal to -4. Sorry, I circled the wrong thing up there. Oh. Make sure you write them in the correct order. Bigger numbers on the right, smaller numbers on the left, negative numbers left of that, more negative numbers left of that. And then pick a number that isn't one of those numbers. You can start anywhere you like. My preference is to start as far right as possible. So I'm going to pick x equal to 5. Because it's more interesting than picking 4, because everyone wants to pick 4. Let's pick 5. So if you plug in x equal to 5, 5 minus 2 squared, is that positive or negative? How about 3 minus 5? How about 5 plus 4 cubed? So I have a positive times a negative times a positive, which overall is going to be negative. You can write out all the factors and write their signs, but I don't like to do that. I think we can say what they are and just keep track of it if it's not too many things. So now, okay, so let me point out. So we're gonna make a guess and then we're gonna verify it. So the 3 came from which of these factors? The x minus 2 squared, the 3 minus x, or the x plus 4 cubed? The 3 minus x. And the power on the 3 minus x is even or odd? Odd. So when the power is odd, we expect the sign to change or stay the same. Change. So we're expecting the sign between 2 and 3 to be positive. Let's check. If I pick a number like 2.5, 2.5 minus 2 is positive. A positive number squared is still positive. 3 minus 2.5 is also positive. And 2.5 plus 4 cubed is also positive. And a positive times a positive times a positive is positive. Great. Okay, let's look at what happens over here. Or let's make a guess. So the 2 is coming from the x minus 2 squared. The power is even, so we expect the sign to change or stay the same. Stay the same. So we're expecting it to be positive. Let's see what happens. So pick a number between -4 and 2. Let's pick 1. So pick 1. 1 minus 2 is positive or negative? Right, it's negative, but then we square it and it becomes positive. So here's actually the crux of what's happening. Over here, when you do a number bigger than 2, number bigger than 2 minus 2 is positive, positive number squared is positive. Over here, when you pick a number smaller than 2, number smaller than 2 minus 2 is negative, but when you square it, it's still positive. So even though we went from the right side of 2 to the left side of 2, this term didn't change signs because it's raised to an even power. And that's why signs don't change when you cross one that has an even power, because it's still going to be positive for that or on either side. 3 minus 1, still positive. 1 plus 4 cubed, still positive. So we still have a positive times a positive times a positive. For -4, we're expecting the sign to change. Let's check. If I pick -5, -5 minus 2 is a negative number, squared still positive. 3 minus -5 is a positive. -5 plus 4 is a negative number. It's -1, and -1 to an odd power is -1 times -1 times -1, which is still negative. So we have a positive times a positive times a negative, which is negative overall. Okay. So now, what's the domain here? Well, do I want the positive parts or the well, actually, I should back up. Do I want to include the endpoints or not? Do I want to include 2 in my domain? If I plug in 2, does 2 make this thing greater than or equal to 0? Yeah, it does. It makes it equal to 0. So when it's greater than or equal to 0, we typically want to include all of my important x values, at least the ones that make it equal to 0 and not undefined. And then I want all the parts where it is greater than, meaning positive. I don't want the negative parts. So here I want everything from -4 to 2 and from 2 to 3. I don't want to write that as 2 intervals because I don't need to. My domain here is everything from -4 inclusive all the way to 2, but there's no, or I'm not excluding 2, so all the way to 2 and continue on all the way to 3. So really I should write this as everything from -4 to 3. And that is my domain, which is also f of x is continuous on the interval from -4 to 3. Okay. However, there's a lot more to say about continuity. In fact, let me grab this one. So when someone asks you where a function is continuous, the question they're really asking you is, where is it not? So let's look at an example. Yeah, let's just grab that one here. Sorry. Sure. Let's look at this function. I think this is, so I think someone asked me this question from, I think it's like problem section 57 from 1.5. Let's look at this function. F of x equal to 1/3 x minus 2 when x is less than or equal to 3, and negative 2x plus 5 when x is greater than 3. This is, oh, question.
The previous problem, why wouldn't we, like, before the -4 and then after the 3, why wouldn't we include the
So
negative, infinity to -4?
So if you pick, so for example, if we pick -5, right? -5 isn't in the domain of this function. So if you actually go back to your original function, you plug in -5, you get -7 squared, which is 49, times 3 minus 5, which is 8. So 49 times 8 times -5 plus 1 is -1, and -1 cubed is -1. So you're getting, if I tried to plug in -5, it's going to be the square root of 49 times 8 times -1, which is a negative number. Is the square root of, I don't know, something gross like 300, I don't know, 392, -392. What's the square root of -392? Not a real number, right? We can't take the square root of a negative number. So this -5 and anything to the left of -4 is not in the domain. You can't plug that number into this function and get a real result out.
So it wouldn't be negative infinity.
Say that one more time.
It wouldn't be negative infinity.
No, we can't. So right, because everything to the left here, right? Whether you pick -5 or -50 million, you're still going to get the same problem. -50 million minus 2 is a negative number squared, still positive. 3 minus -50 million is also positive, but -50 million plus 4 is negative, and the negative number cubed is still negative. So when you plug in -50 million, you get a positive times a positive times a negative, which is negative, and the square root of a negative number is not real. So that's why we're not getting anything over here or anything over here. Same problem. If you pick a number larger than 3, that's positive, that's negative, that's positive. So the overall product is negative. Cool. In order here. So here we have a piecewise function. And if I want to talk about whether or not it was continuous, well, so first of all, I should point out that each of these pieces on their own are just lines. 1/3 x minus 2 is a line, the slope is 1/3, the y-intercept would be -2. -2x plus 5 is also a line, the slope is -2, the y-intercept would be 5. I'm not graphing them yet because I don't want to give away the results. So if I was trying to figure out where is this function continuous, what I'm really asking is, where is it not? Because really, most functions are continuous on at most values of x. There's usually just 1 or 2 or 3 where it's discontinuous. So to figure out if this is continuous at x equal to 3, there are 3 things we need to check. The first thing is, well, yeah, so let me back up 1 second here. We're not concerned about anywhere that's not 3, because if x is less than 3, the function is 1/3 x minus 2, which is a straight line, which is certainly continuous, right? Straight lines are continuous. Same thing to the right of 3. But at 3, you might have this jump from one function to the other. So we're going to check 3 things. The first thing is f of 3 even defined? Because to be continuous somewhere, the function has to be defined there, just like the previous example. Right, we were saying, oh yeah, this function can only potentially be continuous where it's defined on its domain. So is this function defined at 3? Sure. We're told that the function is equal to 1/3 x minus 2 when x is equal to 3. So f of 3 would be 1/3 times 3 minus 2, which is 1 minus 2, which is -1. And I should just point out here that this function, the domain is everything. It's everything from -infinity to infinity. It's defined to be this when x is less than or equal to 3. It's defined to be this when x is bigger than 3. So it's certainly defined everywhere. What about the second thing here is, does the limit as x approaches 3 of f of x exist? This is a function that's defined to be two different things on either side of 3. So we're going to have to look at each of the one-sided limits. So if I look at the limit as x approaches 3 from the left, am I using the piece where x is less than 3 or x is greater than 3? If I'm left of 3. Less. And I always like to think about the fact that left and less will start with L. If I'm left of 3, I'm less than 3. So that means I'm going to use the piece where x is less than or equal to 3, which is 1/3 x minus 2. Now, I will mention when you write this, you should write it as 1/3 x minus 2, not 1/3 times 3 minus 2. And then in the next step, we plug in the 3, we get 1/3 times 3 minus 2, which is the same as it does up here. It's -1. So certainly from the left-hand side, we're going to get -1. From the right-hand side, let's find out. So we take the limit as x approaches 3 from the right of f of x. Now we're going to use the piece of the function where x is larger than 3, which is the second piece here. And that's x is going to, or the function is equal to -2x plus 5. And now we evaluate the limit in the usual way, meaning we just try plugging in the value of x. We end up getting -2 times 3 plus 5, which is -6 plus 5, which is -1. So let me ask all of you, yay or nay? Thumbs up, thumbs down. Does the limit exist? It does. The limit is x approaches 3 of f of x is equal to -1. All right. So now for the final question, although it's not really a question at this point because you can see what the answer is. Does the limit equal the function value? Does the limit as x approaches 3 of f of x equal f of 3? Well, f of 3 was -1 and the limit was -1. So yeah, they're both -1. That means the function is continuous at 3. As well as everywhere else. Because you can do the same work for all the other ones. But the thing is, 3 was the only point that was really in question. Here's what this function looks like if we were trying to graph it. So graphically, things are changing at 3. I know that f of 3 is equal to -1. We just showed that. Let me move this up a little bit so you all can see what's going on here. Let me write the function again. F of x is 1/3 x minus 2, and x is less than or equal to 3, and it's -2x plus 5, and x is greater than 3. So for this top part, that's going to be moving to the left because that's where x is less than or equal to 3. So I would plug in 0 for x to find the y-intercept. And if x is 0, y is going to be -2. So there's my -2. And I can graph this to the right. So here's the portion of the graph where x is less than or equal to 3. And the graph is y equals 1/3 x minus 2. On the right side, the line is going to look like y equal to -2x plus 5. So if I were going to graph that, I could think about where the y-intercept would have been. I'm not actually going to graph it because the function is not defined to equal that when x is equal to 0. But if x were 0, 0 plus 5 is 5. So I can pretend like, oh, there's my y-intercept right there. And it would kind of come down this way like this. And it would hit that point right there because if you plug in 3 there, you do get -1. So coming down like that, now I'm going to start drawing. That's what that looks like. So here's the portion of the graph where x is larger than 3. And they do happen to meet up at the point 3, -1. This graph is continuous, right? You could draw it without lifting your pen off the paper. That's the easy way of saying what continuity means without actually writing out a whole definition. Let's look at another example. And then I promise you, we will write a definition before we end in 10 minutes. I want to give you at least one more example before we do that. So let's say we have, sorry, I know it's always, let's say we have this function, f of x equals x squared minus 5x plus 6 over x minus 2. No, let's just actually, let's just leave it at that. Sorry, I'm gonna write that again. We'll save that for the next one. Let's say our function is just x squared minus 5x minus 6 over x minus 2. Where do you think I might be concerned about continuity here? At what particular value of x? Seems like it could be dicey. Right. So is f of x continuous at 2? Absolutely not. And we know it's not because if you try to see what f of 2 is equal to, you get 4 minus 10 minus 6 over 2 minus 2, which is, did I do this wrong? I think I wrote a different function on the other one. Sorry. I did write it. I'm hiding papers from myself. I think I meant for that to be a plus 6. Apologies. Wow, I really just, it totally disappeared. I know it was a plus 6. Sorry. Either way, 4 minus 10 plus 6 is 0 over 0. And 0 over 0 is completely undefined. Undefined / indeterminate. And it is a fact that for a function to be continuous at a point, it has to exist at that point. If you can't even graph the thing that's happening there, it certainly is not continuous there. Here's what this graph looks like. F of x equals x squared minus 5x plus 6 over x minus 2 is equal to, if you factor the top, x minus 2 times x minus 3. And so as long as x is not equal to 2, this looks like just x minus 3, as long as x isn't 2. So this graph looks like y equal to x minus 3, which has an x-intercept of 3 and a y-intercept of negative 3. Except when x is 2, undefined. So this is what that function would look like. And definitely, it is not continuous at x equal to 2. Here are some words I would say about this function. This function is discontinuous. This function is continuous almost everywhere. Right? It's literally continuous at every value of x except for x equal to 2. But being discontinuous at one point or more is enough to say blanket statement, this is a discontinuous function. Specifically, it's discontinuous at x equal to 2 and continuous everywhere else. Yeah.
So, because I know like on the other limit problems, it would be like, if you had that answer, you would do more work, you wouldn't do that.
I would stop. Yeah. If I were specifically being asked about continuity, I would stop right here.
Okay, so continuity, like no more work.
Right. So to show a function is, so basically once you've failed one of the 3 things that we need, which I'm about to write down, you get to say, you can say function discontinuous without saying anything else. Okay. But let me, I can't believe, oh, there it is. I'm just disappearing papers here. Let's modify this function a little bit. Let's say the function is equal to x squared minus 5x plus 6 when over x minus 2 when x is not equal to 2. And let's say it's equal to 1 when x is equal to 2. So now, the 3 things we're going to check. Now is the function defined when x is equal to 1? Yeah, someone oh, sorry. Well, I mean, it is. That's not what I meant to ask, though. What should I actually be asking about? F of 2. Thank you. What is f of 2 defined to be? Right. Sorry, I got them switched up there. Okay, so great, check. The function is defined at 2. So then we move on to the second thing which is, does the limit exist? In this case, we actually don't need to use the separate one-sided limits because the function is defined to be this thing on the right of 2 and on the left of 2. Right? Since it's defined to be this when x is not equal to 2, that means either side of 2. So if I want to find the limit as x approaches 2 of f of x, it's going to be the limit as x approaches 2 of x squared minus 5x plus 6 over x minus 2, which is equal to the limit as x approaches 2 of x minus 2 times x minus 3 over x minus 2. I can say that x minus 2 divided by x minus 2 is 1, and then this is the limit as x approaches 2 of x minus 3, which is equal to 2 minus 3, which is -1. Does the limit exist? Yeah, it's equal to -1. Be careful. Sometimes people will be like, oh, the limit exists, therefore it's continuous. No. Limit exists, great. The function exists, also great. Are they the same? Definitely not. So the thing is, here we're missing the last part. The limit as x approaches 2 of f of x does not equal f of 2, which means the function is not continuous at x equals 2. So what I did here was I took my same function, which has the same graph, the hole at 2, -1, and I filled in the hole in the wrong spot. I said, oh, when x is 2, the y value is going to be +1. That function is still defined everywhere. Limit exists as x approaches 2, the function exists at 2, but they're not the same value. And you can see graphically here, oh yeah, we certainly have a point of discontinuity. If I wanted to fix this to make it continuous, I would just redefine this to be equal to -1 when x is equal to 2, and then I would be fine. I should really plug this in when I teach this class. Next time I'll do that. Times it. Cool. So let's write down the definition of continuity. So it's usually written as a 3-part definition, although really the last part is all you need. So here's what we say about continuity. Definition. F of x is continuous at a if the following 3 things are true. 1, f of a exists. 2, the limit as x approaches a of f of x exists. And 3, which requires the first 2 parts to be true, is that the limit as x approaches a of f of x is equal to f of a. So this is all you really need to say that a function is continuous at a point. But for the limit to equal the function value, the limit has to exist and the function has to exist. It definitely cannot be the case that if the limit doesn't exist and the function doesn't exist, you're like, oh, well, the limit and the function are equal to each other, though. Not existing doesn't equal not existing. So, right, so if they both don't exist, you're like, whoa, definitely not continuous. Question, what is it? Is it Ashley?
Nikki.
I heard A before. Nikki.
What does that say right below the limit?
As x approaches a.
Oh,
Fair question. Those are A's.